Next, we consider the ancient Babylonian number system. First of all, the Babylonian number system was sexagesimal, base 60, and it was both additive and positional, and it says here that requires some explanation, and it does. First of all, it was positional in the sense that the numbers were expressed as the sum of multiples of powers of 60, and that numbers were written in such a way that the coefficients of the higher powers of 60 appeared to the left of the coefficients of the lower powers of 60. And that's very much the way that we write numbers in base 10 in our Hindu-Arabic system. The coefficients of the higher powers of 10 go to the left of the coefficients of the lower powers of 10. So in that sense, the Babylonian number system was positional. The numerals denoted coefficients of various powers of 60, and the coefficients that represented, or the coefficients of the higher powers of 60 appeared to the left of the coefficients of the lower powers of 60. Now, the Babylonian number system was additive in the sense that the coefficients of the powers of 60 were written additively. The coefficients were written additively. Using these two numerals, this represents the number 1, this represents the number 10. And just for the sake of example, we'll consider the number 1273. In terms of powers of 60, and you can confirm this with your calculator, this is 21 times 60 to the first, which is 1260, plus 13 times 60 to the 0. So let's see how we write this using Babylonian numerals. This much is 20, and this is 1. And this would be times 60 to the first. This is 10. And we have 1 plus 1 plus 1. So this is 10 plus 3 times 60 to the 0. 20 plus 1, 21 times 60 to the first. 10 plus 3, 13 times 60 to the 0. Some further observations about the Babylonian number system. When writing the coefficient of a particular power of 60, the numerals representing 10 were written to the left of the numerals representing 1. Well, let's go back to our previous example here just to confirm that. The numerals representing 10 were written to the left of the numerals representing 1. This numeral representing 10 was written to the left of these numerals, each representing 1. Okay, the next point. The 1 symbol could be used up to 9 times. If we had more than 9 ones, we would simply convert all but the number of ones that were in excess of 10 into 10 symbols instead. So the 1s could be used up to 9 times for a coefficient. The 10 symbol could be used up to 5 times. So why only 5 times? Well, think about it. Let's suppose that we had 6 symbols representing 10. That would represent 60. So we'd have as a coefficient 60 times 60 to a power. But we could rewrite that as 1 times 60 to the power of 1 greater than what we had before. So for this reason, the 10 symbol would only be used up to 5 times. Next point, there was no 0 in the system. No symbol for 0. Well, that could be troublesome. It mentions here that early on in the history of Babylonian mathematics, there was some ambiguity as to whether a power of 60 was to be omitted. To solve this, a gap was sometimes used to indicate a missing power of 60. But this was not always done. Later, a divider was used to indicate a missing power of 60. And here is the divider. This symbol, the 2 arrows pointing upward, that's our divider. It indicates that a power of 60 is being omitted. And let's illustrate this with an example. The number 3,602. Now that's 1 times 60 squared, is that right? 60 squared is 3,600, okay. So 3,602, that's 1 times 60 squared plus 2 times 60 to the 0 power. Now this is a good example because here we have no non-zero coefficient of 60 to the first power. We go from 60 squared to 60 to the 0. So how would the person looking at this notation know that there was no non-zero coefficient of 60 to the first? It's because of this divider. So we have 2 1s here. That's 2 times 60 to the 0. And then we have a divider, which means that the next non-zero coefficient is not going to be a coefficient of 60 to the first, but a coefficient of 60 to the second. So 1 times 60 to the second. This indicates that 60 to the first does not have any coefficient. It's not represented here. And then we have 2 times 60 to the 0 power. One more thing. There was a symbol used to denote subtraction, and this entire symbol represents subtraction. This is essentially the Babylonians' minus sign. The number 9 could be written, well, we'll talk about that later. Let's observe what this is. This is 10. This much is our minus sign, it's the divider, and that's a 1. So that equals 9. And I guess that would beat the alternative, which would be to use this 1 symbol 9 times in succession. Okay. Well, no wonder the Babylonians had a symbol for subtraction. If I had to write this thing 9 times all day long, I'd get tired enough of it to find an alternative as well. Yes, this is 9 right here. A more economical way of writing it would be to write it as 10 minus 1, which the Babylonians would do, using this symbol to denote subtraction. The symbol that followed to the right would be subtracted from whatever was to the left.